Okay, I'm Jeremy Jorgensen, and today I'm going to talk about measurement and variance tests and multiple groups and structural equation modeling, specifically using AMOS. When we want to look at measurement and variance, sometimes we want to know if our construct is measured the same either across groups or across time, or in a number of other situations, for example, across different types of measurement. And so it's important for us, and usually, sometimes this is important to us because we want to understand how a construct is measured across groups or time or something like this. Other times, we're interested in the structural pathways that are between constructs, and in order to isolate structural invariance, we first have to take into account measurement invariance. Because if we don't do that, if we simply look at structural paths and we haven't taken into account measurement invariance, what we might find are differences across groups, and then we won't know if those differences are due to measurement differences or to the structural differences. So today I'm going to talk about how to look at measurement invariance, how we would do that, and some of the reasons why. So the way we do this is we'll impose a constraint that a parameter, like a factor loading, will be constrained to be equal across groups. And then we'll test the model that has a constraint or constraints placed on it, and we'll compare it to the model that is not constrained, where those parameters are freely estimated. And one way we think about these models is that the broader model that has parameters estimated freely is kind of an overall model, and then the model that has constraints is nested within that overall model. And so we're checking nested model comparisons. So we're going to see if a nested model is significantly worse by placing those constraints than a broader model with freely estimated parameters. And we do that using something called a chi-square difference test. Sometimes researchers use differences in the CFI if you have large samples. But we're going to talk today specifically about the chi-square difference test. And the way we do this is we take the difference in the number of parameters being estimated in the broad model versus the nested model. And so however many constraints we placed, that's the difference in the number of parameters. So let's say that we're constraining factor loadings to be equal in one model. We're comparing that to a model that has no factor loadings constrained to be equal. However many factor loadings we're constraining, that would be the number of difference in parameters being estimated by these two models. So we'll take that difference, and that becomes the degrees of freedom for our chi-square difference test. And usually we do one parameter at a time. And actually, I'm going to contradict that, what the slide says, because a lot of times with measurement invariance, we actually will do groups of parameters. So we'll do factor loadings for one construct, or observed variable intercepts for one construct, or error variances for one construct. And that may involve more than just one parameter. So the question that we're asking with the chi-square difference test is the chi-square model fit significantly different for a nested model compared to the broader model, given the number of constraints that we have or the degrees of freedom that we have with this test. And so what we'll do is we'll take the number of parameters different, and we'll take that to a chi-square test. And actually, I'm going to pull one up here. Let's see. So on this chi-square test, let's see, is there okay, here's our, well, we can't zoom a whole lot. At any rate, we'll go to this chi-square table, and let's say that we have a degree of freedom of 1, and so one parameter difference between two models. We'll go to degrees of freedom 1, and we'll go across to the P.05 place column, And we'll see that if there's a 1 parameter difference in these two models, if the chi-square absolute model fit is 3.84 or greater different, or in this case it would be larger or more statistically significant. If it was 3.84 larger in the model that is nested, then if it's more than that, then we know that placing that constraint makes the model fit significantly worse. So we use this kind of as our bar. If we have multiple parameters, let's say we have 5 factor loadings we're constraining, we could go down to this chi-square table over to 0.05 and it's 11.07. So we would look for a chi-square difference of 11.07 or more than that for the nested model, for those constraints to be making the model fit worse, or less than that to say, yeah, we can place those constraints and it does not significantly make the model fit worse. Now, AMOS will actually do this test for you, but I think it's important to understand how it works. And there's a procedure in M+ that I'll show in a different video recording that you can use as well. However, in M+, you kind of have to do this one by hand. There is a walled test of differences that you can ask the program to do. Okay, so we have a chi-square model fit. This absolute model fit does our model that we've specified fit the data. Then we have this chi-square difference test that's used to test nested models to see if one with constraints is significantly worse than the one without constraints. And then we have a chi-square table that we use with degrees of freedom or parameters difference to make that comparison. Okay, there are a number of different tests of invariance that we could run, and one of those is an overall test that simply tests is the variance-covariance matrix for one group exactly the same as for another group. And that is called the omnibus test of invariance. And there are some who argue that this is the one that you should do first. First you do an omnibus test, and then if you find that it's not worse, then you can go in and look at particulars. And then there are other people on the other side of the fence who say, no, you really should never do an omnibus test. You should test specific things. And one of the challenges we run into with invariance tests is that if we examine a large number of constraints at one time, such as with an omnibus test, we may actually mask differences that we might find in smaller parts of our model because the differences in some parts of our model may not be significant, but differences in other parts might be. So it's important, I think, to take a little more specific approach than to just do an omnibus test. Okay, so the first one that usually we do is we test something called configural invariance, where we're checking to see if the same items load for both of our groups in, say, a confirmatory factor analysis framework. So let's say we're testing boys and girls on their introversion and extroversion, and we have a scale of 5 items for each of those. We would want to know, are we getting the same items loading significantly and above 0.4 on a standardized loading? Are we getting the same number or the same items loading for boys and for girls with these constructs? And if you don't have configural invariance, if you don't have the same items, then it becomes more difficult then to actually compare, say, factor loadings when you're dealing with the different animals, like comparing apples and pears. So this would be the first step. And if you don't have configural invariance, then I think you're done testing measurement invariance at that point. Let's say that you do have configural invariance. You do have the same items for boys and girls. Then you can move to the next step, which is testing metric invariance, where you check to see if those items have the same level of correlation for boys and girls. So you're testing the factor loadings across those groups. You may then, if you do have factor loadings that can be constrained to be equal, if you find metric invariance, then you can go to the next step and you can check scalar invariance, where you look at the observed variables for a construct, for a latent variable, and you can test the intercepts of those to be equal across groups. We also have error terms, which some people refer to as uniqueness invariance. So we can test in a measurement model, we can test factor loadings, observed variable intercepts, and error variances and covariances. And I don't see the error variances and covariances here. Okay, I see further, it's down there under weak invariance. If we find metric invariance, scalar invariance, configure invariance, all three of those, we have something called strong invariance. If you have only the factor loadings can be constrained, we would call that weak invariance. Actually, probably more appropriate would be simply to stay with descriptive terms, say in a manuscript that you're publishing, where you say, I had invariance in factor loadings, intercepts, error variances, covariances. Just mention whatever it is that you have invariance in. Other people may or may not know exactly what you mean when you say strong invariance or weak invariance. They probably would wonder what it is specifically that you're talking about. Sometimes we use the terms partial invariance and full invariance. And you can actually go crazy trying to test every aspect of your model. It can drive you crazy, and I don't believe that it's necessary. I actually think that it's best to test groups of parameters at a given time. So you test factor loadings for a given construct at a time, and then you test intercepts, observed variable intercepts, all at one time for one factor, and then the error variances. If you test each factor loading and each intercept and each error variance, and you're doing one at a time, when you get into more complex models, it's just crazy making. And part of the trouble that you run into is, what does that mean then? Like, let's say that you have partial invariance within factor loadings or within intercepts. You then, unless you're developing a measure, and that's the sole focus of your paper, then maybe you have the space to get into that kind of detail. But let's say you have partial factor loadings invariance, partial intercept invariance, partial error variance invariance, and I don't really know that I know what that means, and it just becomes very complex. So I recommend that you work in groups of parameters, and you may run the risk of losing some partial invariance that's in there, being masked by doing them all at one time. But I honestly, in my experience, I don't know that you lose much substantively. So that would be what I recommend. Okay, now I'm going to show some different steps that I would follow to check measurement invariance. And these are informed by Klein's book on structural equation modeling, and also by a paper by Vandenberg and Lance. And the first step would be to check if factor loadings can be constrained to be equal. Now, if you constrain factor loadings to be equal, and you do this chi-square difference test to see if the model fit gets worse or not, if it doesn't get statistically worse when you impose those constraints, then you can move on and test the intercepts. However, if it does get worse, so you can't constrain factor loadings, then you stop right there, and you don't go on to test any other aspects of invariance. You start with factor loadings, and if those can be constrained, model fit doesn't get significantly worse, then we move to step 2. Step 2, according to Klein, is to check the latent factor variances and covariances to be equal. And you would go through the same steps where you would constrain these, check the number of parameters that you're constraining, map those on a chi-square table to see if, and then look at the chi-square absolute model fit between the two models and see if it gets significantly worse by placing these constraints. Actually, I don't usually follow this as step number 2, but that's what Klein suggests. Rather, I go with what Vandenberg and Lantz suggest, where you go from factor loadings straight to observed variable intercepts. So in a latent variable, and I'll show you how to do this, if you find factor loadings can be constrained, doesn't make model fit worse, then I move to the observed variable intercepts, which essentially is testing the mean for your observed variables across groups. So is the average of internalizing on a given item the same for boys and girls? And a lot of times you cannot place this constraint because it doesn't fit your data as well, and so you get worse model fit. But this is something that you can test. So if they can be constrained, then we can move to the next step. If it doesn't worsen model fit. If they can't be constrained, we just stop that right there and report that our factor loadings can be equal across groups. Okay, if our factor loadings and our observed variable intercepts can be constrained to be equal, then we can move to the error variances. And we would do this using the same test where we constrain those to be equal across groups, and then we will test to see if the chi-square model fit gets significantly worse given the number of parameters difference between the overall model and the nested model. So in this, if we can constrain factor loadings, observed variable intercepts, and error variances, and error covariances if you like, then you could say that you have full measurement invariance. And full measurement invariance, like I mentioned earlier, it's rare to find that across groups that theoretically you might expect to see that. You might more commonly see it across time. So it's the same people responding to the survey, only at a different time point. Okay, so how do we do this? The first thing that we do is that we label our parameters, and then we set up what our constraints are going to be based on those labels. And then we compare the unconstrained model with the nested constrained model using this chi-square difference test. And I've kind of already gone through exactly how to do that. So a couple other points before I show an example. So sometimes we do measurement invariance constraints within a single group. Like let's say the boys and girls are in the same group, or a lot of times we see this with husband and wife data where we'll compare parameters across husband and wife, but we want them to be in the same group so that we can correlate them because to account for non-independence between husbands and wives in the same data set. A lot of times we'll do this in multiple groups, in which case we would need to set up the groups, specify the data for the two groups, using the grouping variable, grouping value. I'll show you how to do this, and then you constrain across those groups. Okay, a couple of additional points. When we place constraints on our models, the unstandardized parameters are equal. However, our standardized parameters may not necessarily be the same across groups. And the reason for this is that the calculation that goes into what the standardized coefficient is based on the sample that the data is used for. So if you have boys in one group and girls in another group, the standardized coefficient may be different for the boys than for the girls based on the data that's going into those coefficients. So don't be surprised if you see that. The other thing we have to be really cautious about is when we specify multiple groups, we need to know, do we have a large enough sample to run the model that we're running? it essentially splits our sample in half when we have two groups. So let's say our overall model has boys and girls in it, and let's say that we have 200 boys and girls, and we have, let's say, 20 variables in our model, then we're just fine. But if we were to split those into two groups where we have 100 boys and 100 girls, if we still have 20 variables, observed variables in our model, it's probably not going to run. We're going to need something like 10 observed variables for each group. So be aware that sample size is an issue. One other thing that's not on this slide here is that sample size is also an issue in that in smaller samples, it's more difficult to detect invariance tests, or significant invariance. So you might be more inclined to examine single parameters at a given time in smaller samples, in smaller models, but that's probably more so the case when we're testing structural invariance, which I'll get to in another lecture. So know that sample size is an issue for invariant tests in general and when you break up into multiple groups. Okay, and here are some references where you could look up more information about measurement and structural invariance. I'm going to go ahead and move to an example now in AMOS. Let's see. Okay, so I've got this data set here in SPSS, and I'm just going to open up AMOS. I have these latent variables that I'm going to create of closeness to a grandparent, and first I'll look across time, and then I'll look for children in two-parent families versus those in one-parent families. And okay, this is just taking a minute to come up. Okay, so let's see if I can specify the right data file. Okay, so I'm going to do a couple things here. First, I'm going to go to the interface properties, and I'm going to switch the size of the little drawing template in AMOS so that it is landscape. And what that will do is it just widens the amount of space that I have to put my model in. Next, I'm going to just move this over a little bit, and then I'm going to copy it and just have one of these be time 1 and the other one be time 2. And I guess when I do that, I'm going to have to go in and change a few things, like these errors they're going to be labeled as the same thing. So I'll change this to E7, 8, 9, 10, 11, 12, and I'm going to have to change this one to F2. And then when I look at my I'm just going to change, let's see, that's for time 2, and that's also for time 2. So I'm just going to change these ones to time 1. Okay, so F1 is for time 1, F2 is for time 2, and I would correlate these two. Okay, so now we're going to test measurement variance across time. This factor represents closeness to a grandparent at time 1 as reported by youth, and this represents closeness to a grandparent at time 2. So the first step we're going to do is look at factor loadings. So I'm going to deselect everything and go ahead and click on the first arrow, And under object properties, under parameters, I'm going to label this FL1. And let's use a little convention here so that we know what they are. So we'll do FL1 underscore 1. And I'm just going to copy this so I can paste it easily into the next ones. This one will be FL1 underscore 2. So factor loading time 1, number 2. Number 3, factor loading number 4, factor loading number 5, and number 6. Over here, we're going to call this one factor loading 2 underscore 1. So time 2, factor loading number 1. And let's see, copy that. So we'll have factor loading 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. Okay. Now, while we're here, I'm going to go ahead and label the intercepts. So let's see. Okay, notice how the intercepts, it's not letting me change a parameter on the intercepts, and that's because as of right now, I have not checked the box in AMOS saying I want to estimate means and intercepts. So I'm going to go up to Analysis Properties and click on Estimate Means and Intercepts. I'm also, while I'm here, going to check in the output to get standardized estimates, and that should be good for now. Okay, so now the intercept, we're going to call this INT1 underscore 1, and we'll make the next one 1 underscore 2, 1 underscore 3, 1 underscore 4, 5, and 6. And this one we will do int 2 underscore 1. And this one will be 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. Okay, and last we'll go to the error variances and make sure you don't change the mean from 0. And we're going to change just when you click on the round part here of the error term. You don't ever want to change these regression paths going from the error term to the item. Those always have to be 1, or else the program will tell you that your model's not identified and you have to impose an additional constraint, but you can impose a million constraints and it will never work. Under variance here, I'm going to call EV1 underscore 1, and then 1 underscore 2, underscore 3, 4, 5, and 6. And over here, I'm going to do 2 underscore 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Okay, so now all my measurement parameters are labeled, and I am going to go into this default model window, and I'm going to, because I labeled the first factor loading, which is our scalar item that is set to be equal to 1. Because I have taken away that constraint that those are 1, I need to re-specify that, or else these models won't run unless I were to make some other constraint like setting the latent variable variance to equal 1. But we're just going to say that we're going to go down here and say that FL1, 1, 1, and 2, 1 equal 1. So when you double click on these, it'll put it out there, and when you double click on another one, it'll automatically put an equal sign between them. So once I do that, this is for my default model. This is going to be my broader model. And now I'm going to create a nested model that has more constraints. Okay, so I'm going to highlight this because this needs to be in all of my models here. And I'm going to copy that. And I'm going to click New. And model number 2, I'm going to say this is the factor loadings constrained. And I'm going to put in this first one equals 1. And I'm going to say FL212 equals FL22, enter. FL13 equals 23, enter. FL14 equals 24, enter. 15 equals 25, enter. 16 equals 26, enter. And I'm going to copy this all for the next one. Okay, so this would be to test whether our factor loadings could be constrained to be equal. Now I'm going to click on New, and I'm going to create a model here that has factor loadings and intercepts constrained. And I'll paste in my factor loadings. And now I'm going to constrain my intercepts by saying 1, 1 is equal to 2, 1, enter. 1, 2, and 2, 2, enter. 1, 3, 2, 3. And you could type these out if you wanted to. I just think it's easier sometimes to just double click on these. Okay, so there's my intercepts. I'm going to copy all that for the next one. And so we have factor loadings, intercepts, and now we're going to add error variances. Okay, so we'll put up here factor loadings, intercepts, and error variances constrained. And I'll now add the error variances here by saying 1, 1 equals 2, 1, enter. 1, 2 equals 2, 2, enter. 1, 3 is 2, 3, 1, 4 equals 2, 4. 1, 5 equals 2, 5. And 1, 6 equals 2, 6. Okay, so now I have 4 models. I've got the default model, the factor loadings, the factor loadings and intercepts, and factor loadings, intercepts, and error variances. Each one of these is nested within the one above it. And so we can compare each one with the model above it. And we'll start with comparing the constrained model to the default model. Okay, so I'm going to go ahead and estimate these models. And I see the OKs here in that little window there, so I know that it's that they ran. And that's essentially the same as seeing minimum was achieved in the output. I'll go ahead and go to the output here. And let's see. I'm going to, so here's that minimum was achieved. That means our model ran, got 53 degrees of freedom. So our model did estimate. If we wanted to, we could check model fit here. And it's a good idea when you're doing nested model comparisons to check out the chi-square for each model along with the degrees of freedom. This tells you how many parameters were estimated and what the differences were. Well, number of parameters is right here. So let's say we have 37 parameters with chi-square 513. We go down 5 parameters, that's those factor loadings we constrained, and the model fit gets worse by 150. Now going to that chi-square table, just eyeballing it, we know that this one's going to be significantly worse. Going down another 6 parameters, the model fit gets substantially worse. Again, it looks like we're not going to be able to constrain any of these without making the model fit worse. In other words, it looks like closeness to a grandparent, that measuring that, at least in terms of factor loadings, intercepts, error variance, it looks like they're not going to be the same from wave 1 to wave 2 of the data that I'm showing you. Now, there is a formal test of this, and we'll go down, we'll go down to that test. We could just click here on Model Comparisons, where we have nested model comparisons, assuming the model default to be the correct one, to be the broader model. Does constraining factor loadings make the model fit worse? Well, we have 5 degrees of freedom with this test, like we've been talking about, with the chi-square difference test, and a chi-square difference of 163. So it's basically just doing the math for you based on the model fit table that we just looked at above here. It's just doing this math for you. And then it's saying that that actually is a significant test, meaning that the model fit is significantly worse. And if we go to our chi-square table, we see that with 5 degrees of freedom, it has to be only 11.07 difference or higher, and it's significantly worse. So we see that it is significantly worse here. So we're going to not be able to constrain factor loadings, and because we can't constrain factor loadings, we'll just stop right there. If we could constrain factor loadings to be equal, then we would, let's see, if we could, let's go to this model comparison. Okay, then we would assume that the factor loadings constrained to be equal is correct, and we would look at factor loadings and intercepts. And with 6 degrees of freedom, we have 436 chi-square difference cannot be constrained. If we scroll down, whoops, missed the bar there. If we scroll down, if we had factor loadings and intercepts that could be constrained, then we could compare that model to the one with error variances constrained, and we would see that with 6 degrees of freedom, it has a change in 46. That one's closer, but it's still way too big. If you look here with 6 degrees of freedom, we're seeing 12.59 and higher means it's significantly worse. So we can't constrain those to be equal. Okay. I'm going to go ahead then and take the time to variables and delete them and show you how you would set this up in multiple groups. Okay, so let's say that this group is going to be for group number 1, we'll say is single parents, and group number 2 will have kids in the homes of 2 parents. And so now we have our 2 groups set up. We need to go to our data file and specify that the single parents, with the grouping variable, we use family structure, and the value that denotes whether you have single parent is 2. So, and we have 165 single parents, and we have kids in single parent homes, and then 335 kids in 2-parent homes. Okay, so now I've set it up so that group number 1, using family structure variable value number 2, specifies those, and the other with 2 parents, family structure value number 1. Okay, so now I've set it up so that there are 2 groups here, and we can click back and forth between these 2 groups. Now right now they actually look exactly the same, and we're going to change that because we want to compare things across the groups. And there's a button that we have to click on in AMOS to do this, and I call this the button of no return, because once you click it, you can't go back to how things were. You have to start over basically with your model. So don't click this unless you really want 2 groups to have different diagrams. That's the button we're going to push. And we find that under View, Interface Properties, Miscellaneous. And it's right down here. It's the only one that's not checked already. It says allow different path diagrams for different groups. We're going to say we want to do that. And it says currently every group is required to have the same path diagram. If you remove this requirement now, you will not be able to reimpose it later as long as there are multiple groups. Do you really want to allow different groups to have different path diagrams? And we're going to go ahead and say yes, we do. The reason you want to be careful with that is because if you inadvertently change something about your diagram that's not supposed to be changed, then it can be a problem. But we're just going to leave group 1, we're going to leave all these labels as they are, And we're going to go into group 2 and just change these labels to, we don't want to put a number at the beginning of the label. Let's see, but we could put a T for 2. So let's go ahead and do that. So all of our parameters that are in the group 2 are going to start with a T. So I got the error variances, now the intercepts. Oops, that didn't work. Okay, and now our factor loadings. In AMOS, it's kind of hard to sometimes pinpoint these lines, and so if you go to the head of the arrow, that's usually a little fatter, oops, then it usually works a little better. So let's see, have I got that one? Factor loading number 4, number 5, and number 6. Okay, so now my two-parent, all my parameters in the two-parent group start with a T. So we need to go back to our models, comparisons, and say this one's going to have a T. And actually, the other thing I'm going to have to change is it's not at time 2. So it's going to be FL1 underscore 1 equals TFL1 underscore 1. Okay, let's just go here to our diagram and make sure that that's correct. So if we look at group number 1, we have FL1 underscore 1. And group number 2, we have 2 TFL1 underscore 1. Okay, so our default model, that one's correct now. Our model number 2, we've got to change all of these 2's right here to be 1's. And then we're going to put a T in front of each of these. And I'm just going to copy this and paste it in the place in the next one. Factor loadings and intercepts, so I'll go ahead and replace that. And then for our intercepts, here I'm going to change these all to 1's. And then put a T in front of each of them. And now I'm going to copy all of these. Whoops. For our next group, and I'll go ahead and trade these out, and okay. So I've got everything relabeled now for my two groups. And I'm going to go ahead and close this. And I think I'm ready to run this model. And it looks like all 4 of them ran. And if we wanted to look at our output here, we could click on this red arrow and we could click through these and say, okay, how do these change? Okay, and we'll go ahead and go to our text output and look at notes for model. Minimum was achieved for our default model. And if you were to scroll down, it would just take you through each of your models with the different parameters for the model. There's group number 2 for default model. And then we have, this is the model number 2, factor loadings constrained, group 1, and then group 2. And it just goes through everything there. And we could go in and look at the specific parameters. What we're going to look at first is the model fit. We want to look at this chi-square thing. So with 5 degrees of freedom, we're constraining 5 factor loadings to be equal. And we see that from boys to girls, it changes the chi-square model fit about 4 points with 5 degrees of freedom. And if we go back to our chi-square test, 5 degrees of freedom, 4 points, that is not significantly worse, okay? And we see here 6 degrees of freedom because we got 6 intercepts. We notice a difference of almost 20. So it looks like maybe that one's going to be different. I'm just eyeballing these. And then another 6 with a difference of around 40. So I'm guessing right now that factor loadings can be constrained, but intercepts and error variances can't. Let's go ahead and go down here. Oops, I keep doing that. Go down to our model comparisons. Assuming the default model to be correct, the factor loadings constrained is not significant. It does not make it significantly worse. And that's just that chi-square difference test. Assuming factor loadings to be constrained to be correct, can you constrain intercepts? Well, 6 degrees of freedom, change in 19, and the p-value is significant. So we cannot constrain the intercepts. And since we can't constrain the intercepts, we stop right there. We don't even go and look at the variances, the error variances. If we could constrain the intercepts, then we could look at the error variances. Something that I haven't dealt with here today, you could go in and test the variance of the latent variable in addition to these parameters if you wanted to. But I would save that until after you've done all of these, and I think you'd have to think conceptually about what does that mean for the variance of that latent variable to be equal across your groups, whether you were going to constrain that or not. Okay, so that's all I have for today on measurement invariance, placing constraints in AMOS across time and across groups. Hopefully, I went fairly quickly, but you could rewind this video or do it in slow motion or stop it at different places to be able to do that with your own data. I hope you find this helpful. Thank you very much.